So today's session, what we're going to work on is developing a common language, identifying resources that support core instruction. One of the things that we learned from our friend Cain, who remembers that message that we learned from Cain? What was on the vomit bag? Anybody? What was that thing that was on the vomit bag that he was number 3 on the vomit bag? Go ahead. Yeah, start with what you have, right? And we've talked about what you have is naturally curious kids in front of you every single day in school. And so it's how do we engage these naturally curious kids that are in front of us every single day in school. And then along with that, how do we identify the resources that we currently have? We'll get this fixed because I know that's still got a little ring to it. Identifying resources that support the core instruction. So today is workshop 5 of 5. For those of you that have been here all 5, you know what all 5 of these look like. But if this is your first time, back in October, we discovered the role of STEM. November, industry and higher education, elementary skills required for college and career readiness. In December, scientific habits and inquiry. January, finding STEM time on learning. And then now, today, working with a common language. Important, important, important. We want to make sure you mark your calendars, particularly as you guys being the pioneers of this project that we've been working on. We have our STEM Summit, first of its kind ever in the state, and the fact that it's an elementary STEM Summit. We know that the state puts on a STEM Summit, and that's for K-12 and business and higher ed and so on and so forth. This STEM Summit will be strictly focused on elementary educators. It'll be an opportunity for elementary educators to come together and celebrate innovation. We're in the process of planning this, and we're going to stay in touch with you over the course of the next couple of months to let you know how this is going to unfold. Working on finding some keynote speakers to come in and different presentation sessions for you as well. That's June 4th, 9 to 2:30. We'll throw another reminder of this up as we get to the end of the session today. So our schedule today, for those of you that have been here before, you kind of know the rhythm of the day. The morning session is from about 9 to 11:15 or so. 11:15 we stop for lunch. Again, lunch is here on campus. It's cash only. There is an ATM in the cafeteria. A lot of you often will bring lunch and eat somewhere around this general vicinity. But we have an opening activity that Francis is going to take us through. It involves this. That's why I've been holding this, to remind myself. Lesson efficiency, establishing a core of instruction, where do auxiliary resources belong, common issues with STEM lessons, making common core connections, and then talk about UBD. So a couple of us were talking about UBD before the session started today. And then this afternoon, really focus on sort of STEMifying. We developed a new verb. STEMifying your lessons, taking lessons that you currently have and STEMifying them up and starting with what you have. So with that, I hand it over to Francis, who's going to take you through this activity.
Can you hear me? Oh, yeah. And this afternoon, it's not just STEMifying our lessons, but that's the major focus we're going to start with. So don't feel like if you didn't bring a lesson that lunchtime you should go home. Come back. There's going to be plenty to do. Starting with what you have. So one of the things that we have here today are tennis balls. And we've been talking about STEM practices. And so we wanted to sort of start off with an activity, putting you all in teams of 5, maybe 4, depends if one of your teammates didn't make it due to the snow, to figure out how many of these tennis balls would fit in this room. And we're going to give you a good amount of time to figure this out. So what do you think? Where would you start? Yes. Okay, some key questions. What's the volume of the tennis ball? What's the size of the tennis ball? What's the volume? What's the size of the room? So on your name tags, you have a number in the lower corner. I don't know if it's the left or the right. And whatever that number is, there's another number starting with number 1, kind of going around the room this way, someplace. If you can move to your number, meet your teammates, and then send somebody down to grab a tennis ball. We've got 1 tennis ball per team. And you're going to have to figure out, and again, we're trying to find who comes closest, so.
You'll win the tennis ball if you get the right answer.
Yes.
So we're going to give you plenty of time for this. This is not like a guess. This is what is the process it takes you to figure this out. That's what we're interested in. So the number is great if you can get to the number, but we're going to be more interested in your thinking that got you to that number. So look around the room and you'll find all the different numbers. So take a look at the results.
Okay. Can everybody read this?
In case you can't read it, group 1 is 11,908,000. Yeah, there we go.
I think group 12, yeah, group 12 combined, so nobody's cut off.
Group 2, 336,000. Group 3, 3.6. Group 4, 2.2 mil. 2.9, 5.2, 1.1, 4 mil, 370,000, and then 10.6 million. So before we reveal the answer, dun, 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 we want to hear everyone's thinking. So Francis is going to take you through and ask our groups, and we want to learn. We saw lots of different techniques being used. We saw the foot method. We saw the width of arms and the height, and we saw someone standing here, and I think it was if we stacked 10 of you up on the wall, it would be that many people. And so we saw lots of different strategies, but
the big thing we want to talk about is what STEM practices did you find yourself using to kind of get through this task? Just feel free to, yes. So there's lots going on here. So it sounds like, yes, lots of using models. So developing and using models. Where were we developing and using a model in that example? Where did you hear a model being developed and used? Okay, the prisms, right? So there's rectangular prisms in here. There's also triangular in the back, right? So you could actually, there's several ways of doing it. You can get into the complex shapes that are above the incline over there. Or what you can do is say, this whole main section of the room is a rectangular prism, and we can subtract out the triangular prism, which represents where you're sitting on the incline, and then add in the rectangular prism that represents that top section, and add in the rectangular prism that represents the window, if you remembered the window. So that's one sort of developing and using a model for picturing the room in terms of shapes that we know how to calculate easily, right? How many people were thrown by not having any rulers or measuring? How did you measure?
No, we improvised.
You improvised, okay. That process of taking the tennis ball and relating it to something else, you're creating a tool. And you're developing and using a model for measuring. Right? So if you figured out that the length of your paper is approximately three tennis ball diameters long, or 5, okay, depending on which way so 5, and then you're going around. Planning and carrying out your investigation. There was and it's interesting watching the group behavior, because generally we think about brainstorming, norm storming, and form storming. And the first bit, everybody was sort of getting together and say, okay, how are we going to do this? All we've got is a tennis ball. Then the next bit was, okay, well, here's the only practical way we can see to move forward, or a few options. And people started moving out and actually so they went from planning to actually starting to carry out the investigation. And then people started going back as they were forming their conclusions, saying, this doesn't make sense. Maybe they were checking with another group. Like, our number is not just not close, it's way up. So they would go back and say, but let's go through these one by one. So if we had asked so we're asking a question here. Is this science? Is this engineering? Here's some people confidently saying yes. I see some other people who are kind of like, I don't think so. And some people who are kind of in the middle. What's the argument that this is science? Does anyone want to give us an argument that this is science? Scientific investigation? But what would make it qualify? Why do you think that this qualifies as a scientific investigation? we're starting with a question. So science starts with a question. Engineering starts with a problem. So if we had framed this differently, maybe something around, trying to come up with it quickly here, but like something along the lines of, can we produce enough, or actually, it's tough to kind of fit it into a problem. But if there was some reason that we needed to store tennis balls in here, if instead of an auditorium, this was some kind of tennis ball silo from hell, I don't know what that would be like, like the ball gym at what is it, Chuck E. Cheese. Okay, that's a different story. But in this case, we had a question. So we're trying to answer the question. So we can maybe eliminate the engineering aspect. What is the new knowledge that we gained from the experiment that in theory, the number of tennis balls that will fill this room. Now, so what I'm trying to say here is that for science, you're starting with a question. For engineering, you're starting with a problem, but very specifically, how many tennis balls will fill this room falls into the science side. However, is it standards-based? Is there a standard related to tennis balls in a room? No, no, it's a context. However, it's using all the STEM practices. So this actually has a whole bunch of math frameworks underlying it. So when we talk about kind of teaching across the curriculum and integrating the different content areas, all of these STEM practices are related to the new STEM standards. So it is science from a standards perspective there, but it's not, the tennis balls themselves will never be, it's not, you don't need to know how many tennis balls fill a room.
So I think if you make that connection to kids in the classroom, right, it's the journey versus the destination. So of this, what's more important, that we know it's X amount of tennis balls that can fit in the room, or what it took to get there? It's the process, right? And so, and this is something we're going to talk about a little bit later today. The content is just a vehicle to practice process. And I think that's a switch. That's a cognitive switch for a lot of us in public education, because we get content drilled into our head because MCAS. You have to know this, you have to know this, you have to know this. If we can make that cognitive flip in our head and understand that the content is just a vehicle for practicing the processes in the way that we want kids to think, we really have an opportunity to change how we're handling education, because then the content will solve itself. It no longer becomes memorize the content. It becomes, the more we can practice this pathway to get to the content, you'll be able to solve any content. If you can figure out how many tennis balls fit in here, we can figure out how many tennis balls fit in the room where we have the food, right? Where the lunch and the coffee and all that stuff is served. Mm-hmm. So once you know that, it's the skill of figuring that out, that art and science of knowing what the process is. So I think that's really part and parcel of this is, it's not the end result, it's the road to the end result that's important.
Right, and just sort of looking through these, just getting beyond the first one. So we asked a question, so it was science-oriented. We developed and used the models, planned and carried out some investigation. You translated that ball into something that you started measuring the room. You translated that into some sort of a relationship between the volume of the room and the number of balls that would fit in that volume. You analyzed and interpreted the data. So whatever your calculations were, some people were saying that they thought that their number wasn't reasonable. They went back to the drawing board. Using mathematics and computational thinking. So again, relating you're not just measuring in one dimension, you're measuring in 2 dimensions and then also in 3 dimensions. Constructing an explanation and designing a solution. Designing a solution would be for engineering. So constructing an explanation. Someone was saying they could argue their point. Engaging in argument from evidence. So when I show you the numbers, I don't doubt that some people are going to say, well, did you account for this? That's where the argumentation from the evidence comes in. It's obtaining, evaluating, and communicating. So let's take a look at what the figures were. All right. So the real...
Wait, don't give the real one yet.
Oh, okay.
I'm just curious, real quick. What were some other thought processes that happened? What are some other ways folks figured it out? I just want to hear from some other groups. How did you, some people shared a couple of ideas. Some other groups share, how did you get there? I want to know what the path was. everything you've learned on your life up until today at 9:20, right? Every experience that you've had, you brought to this event. So you've had different experiences than you did, than you did, than you did, than you did. School experiences, life experiences, conceptual experiences, how you think about things. And so when you think about the complexity of that, right, the complexity of the group dynamic working together, and then tied in with the complexity of everybody's different level of thinking, and so you've got all these sort of tributaries and rivers, right, flowing in, and at the end it's just, here's the number. And so that's the fascinating part of, I think, what we do in school, when you think about teaching and learning and how it all comes together within your classroom. But again, the content is the vehicle to practice these things. And I think that's really the mindset that we want to try to set today. So, we ready?
Should we reveal it?
We reveal.
Okay, so.
Someone, let's see, let me look real quick. We have one group that's really close. .7.
So if you...
Now you're just showing off. Good job.
Really, really
Group 3 is
close
right
one.
here. This is group 3 over here.
Yeah, so how is that determined? So the simple method that I used was I took very similar to what one or two other groups did. Basically, if you look around here, all of these panels are standard dimension, and basically you can calculate the length and width and height off of all of those, and even to the point of this white space on the ceiling. And what's interesting is that while the furniture, may matter, may not matter, if you were trying to get to, the nearest 100,000, it doesn't change it a whole lot, because like even this window area right here, this window area is only 34,000 tennis balls. So, it's a lot of tennis balls if you had to pay $1 each. But in the scheme of things, it doesn't really change the overall number too much. And my thinking was to go ahead and create one rectangle out of this room, subtract out the triangle there. And what's really neat about that is that you can get the dimensions of that triangle right off of these panels here, just kind of vertically and horizontally, because the two of these panels add up to the length of two of these panels add up to the length of one of those panels, and so on. So anyhow,
we have to give Group 9 props too, because they were at 4 million. They were right in the ballpark as well.
Yes,
so
and I
Group
thought there
9
was someone else that was really. Group 3 is really close too. Sure. I'd say Group 3, Group 9.
Yeah.
Right.
So how many tennis balls fit in a cubic foot?
I didn't calculate that. A tennis ball, the diameter of a tennis ball is 3 inches.
There's a tape.
Well, that was
there.
it's approximately, we'll say approximately 3. The other thing, though, is, the number, the thing is one, the number doesn't really matter. But aside from that, it's how you get the number. It's the journey.
Yeah, I know.
But
he's got it down to a tenth. Exactly.
No, but there's things that actually my number is not accurate for several reasons. One is that in real life, the mass of these tennis balls would actually compress,
right.
And so we would fit a lot more than that, simply because the ones on top would be compressing the ones on the bottom. The other thing is, and actually this happens on a molecular level with iron and steel, that when tennis balls, like you see in this box here, that they don't stack on each other perfectly vertically, they offset. So as you get lots of layers, you actually create more opportunity to fit tennis balls in. So even the number that would fit in a cubic foot would not be accurate relative to the number that would fit in a cubic yard or larger.
Good.
Yes, but I think for a ballpark estimate, it's not.
We're actually going to do this during the STEM Summit. So we're going to fill this room. Priscilla, is that okay? We fill this room with tennis balls and we'll count. Exactly.
But the key is that we all had an opportunity to use those STEM practices and see them in action.
So why don't we allow folks to go back to their normal seats so you can find your notes and everything. So just switch back and we're going to continue with the presentation.
Okay, so second grade standard. Third grade standards. These are all math standards that were related.
These are right from the frameworks, Common Core. And if you just kind of take a quick look, how many grade 2 folks we have in here?
There's actually a grade 1 standard as well, although to be able to really do this activity, you need the grade 5 standard, so it's not like you can go back to your first graders and say, fill the room with tennis balls.
How many grade 3 people? A couple of grade 3 folks? Okay.
How about grade 5 folks? You can see recognize volume as an attribute of solid figures, understand concepts of volume measurement, measure volume by counting unit cubes, using cubic centimeters, inches, feet, and improvised units. Okay, that's what you were doing, improvised units. I guess I should back up, 1 second here, just to take a look at the grade 2 here. So the grade 2 standards, I'll just read it because I know it's so small. Partition a rectangle into rows and columns of the same size squares to count and find the total number of them. So you did that with the triangles. Or if you made a little improvised measuring tool and you used that to find the tiles on the wall. Interpret products of a whole number. Use multiplication and division within 100 to solve a word problem in situations involving equal groups. Determine unknown whole number in multiplication or division equation. It depends on your approach. Relate area to the operations of multiplication and addition. Find the area of a rectangle, whole number sides. So, if you were able to, which I didn't do, Google the exact diameter of the tennis ball, I more estimated. You might have not had a whole number. Use tiling to show in a concrete case that the area of a rectangle with whole number side lengths. Use area models to represent the distributive property of mathematical reasoning. Recognize area as additive. All of those third grade standards, all of those were things that we were using. We just mentioned the recognizing volume from grade 5. Using improvised units. Relate volume to the operations of multiplication and addition and solve real-world mathematical problems. That's what we did, involving volume. Find the volume of a right rectangular prism with whole number side lengths by packing it with unit cubes. Apply the formulas length times width times height. Volume equals base times height. Probably most people did that. That's what I did. Recognize volume as additive. So again, by breaking the room into segments and adding the volume of this segment to that segment. Solid figures composed of 2 non-overlapping right rectangular prisms. Okay? All of those are things that we did. All math standards. So that's where I come back to that thing where I say, well, is the science, yes, in its structure. Is it a science standard specifically? No. It's mathematical standards. The elements of it that are science standards are those practices, so that's where you're creating a synergy there. I saw a hand over here. Yes?
I was just saying, if you wanted to modify this for a younger grade that doesn't know volume yet, you could just say how many tennis balls will fill the floor space.
Right.
That would be surface area, yeah.
Yeah.
If you don't have the fifth grade
Yeah.
benefit of volume,
Yep.
Yes.
you just do surface area. Then they could use the tiles on the floor to figure out over exactly
Yeah.
inches, to modify it, to bring it down to a lower level.
Sure, and if you even think about estimation, I mean, at the early grades, K1, 2, I'd even push them a little further up, but pre-K, K1, if you just took a smaller bin than this,
Right.
and let's actually figure out, first of all, let's look at a tennis ball, and let's try and picture how many of these would fit in here, and then let's actually put them in there. So let's compare our estimate to the actual number. And then what were the things, just like those tennis balls not stacking perfectly on top of each other like this, they offset, maybe comparing bins of 2 different sizes just to make the observation, to actually physically discover that.
Plus just the practice of estimation
Yep.
before you start
Correct.
at your actual number, so that when you look at the number and you say, oh, that doesn't seem right.
Right.
Just that piece in math alone, knowing whether your answer is reasonable, and real life lends itself to that so much more than paper.
Yes, exactly.
Well, and every
exactly.
time you do that, and to your point about at a younger grade looking at surface area, every time you do that, again, you're giving kids an opportunity to think. right? It's not just giving them the information, they're thinking. And the more that we can get them to think, the better served we're all going to be.
If you could picture these were water molecules, the reason that salt water, has a different freezing and boiling point than fresh water has to do with the salt actually getting between those molecules and causing issues with the polarity and the way that they attract. And what's interesting is you could actually fill a container like this, and you fill it all up with the tennis balls. Well, what else can we fit in the space that's left over? So, we could keep going after. We could maybe, depending on the age of the students, you could start maybe using marbles or something of that nature. And then, well, if now the space is between the marbles, what can we fit in between those? And again, that's like the concept of mass. People think about the concept of mass, and they say, oh, I don't know, we just talk about weight. Well, guess what? The reason mass matters is for that exact reason, that this space where we can fill it with all these tennis balls, that same space can be filled with tennis balls and marbles and sand and water, and we can keep going and going and going, packing more and more matter into that one volume, depending on what it's comprised of.
Yep.
So one of our favorite things we always love to talk about in elementary education is KWL.
What is KWL? Good job.
So maybe some of you, as scientists, as you were investigating the room, you were too shy to talk about using the scientific method, starting with that question, and researching amongst your team what you knew relevant to the question to be able to test, to come up with a hypothesis about how many tennis balls fit in this room. Fit into a KWL type model, what you want to know is the answer to that question. You want to know about that hypothesis. Is it true or false? Okay, you're developing an experiment, procedure, materials, all of the scientific diagram data, that all feeds what you want to know. The conclusion's sort of on the edge, right? Because that's where you come to a conclusion about your hypothesis. So you want to know that, but what you want to find out or what you want to discover really is the data. Once you have the data, that forms a conclusion. So that conclusion, maybe you could argue either way if that is what you've learned or if that's what you want to know. But what you learn is definitely the conclusion, and you might be able to lump the data in there because it's the product of the experiment. So somebody who was sitting up here earlier was saying how this is science because we have evidence to support our claim. We went through and we actually did an investigation. We did an experiment. We gathered data. We have that evidence, and we can now use that to support our claim about what the number of tennis balls that would fit in this room. That's what you've learned. Okay? So it's not completely linear, as in, here's the things I know, here's what I want to know, this one thing, and now that we did some whatever, here's what I've learned. You can actually unpack it into the different steps within the scientific method. And when you think about those processes, the practices that we were talking about earlier, all of those practices happen within the different process steps in different combinations. So you need those skills to be able to progress through an investigation. So we could just call this the investigative process, and that would fit fine.
Yeah, just thinking about the whole notion of knowledge, and someone brought this up a few minutes ago. What we do with knowledge, right? I think that's often a hyper-focus in schools. It's what do we do with the knowledge? And I think we have to spend some time on knowledge creation as well. How is the knowledge created? How did we get to that point of knowledge? And so if we're creating new knowledge in a class from a discovery and experiment, having that focus on how the knowledge was created, again, the road to get there, we've got to give equal time to that because it's just as important.
And I think people get a little thrown by this because you see how you're starting with something that you want to know, but then you need to relate what you already know to it, but then you have more things that you want to know. So it's a little bit confounded. When you look at engineering, so science, question, engineering, it's a little more straightforward. So what you already know is, and you can maybe debate a little bit about the problem, but you know the problem, you know facts relevant to the problem. You can research the problem, what materials you have available, ideas about possible solutions. But once you come into those ideas about possible solutions, you're going to actually be testing those. So that's where you start. You're kind of an investigation here. So you're identifying one, you're diagramming and building it, you're testing it, you're gathering the data as a result of the test, and you want to know whether that prototype solves the problem. How well does it solve the problem? So that's where what I want to know kind of overlaps with the conclusion here a bit. Would you refine it or replicate it? If you replicate it, great. Go patent it, go whatever, and off you go. And if you'd refine it, then you go back up the chain and you go through again, maybe identifying a different solution or maybe redesigning the prototype and continuing back through. What you learn is how well fit that prototype is, or that technology, that solution is to solving the problem. Okay? And that's because you need to generate the data in order to come to any type of conclusion. So engineering's a little, in some ways, it's more linear. You can see what I know, what I want to know, what I learned. Science, not so much, but it becomes nonlinear when you have to go back and repeat. And that's why sometimes people think about engineering as like a circular, like a cycle process.
And I think we said this in previous sessions, and I think it's 100% worth repeating. I think a big part of what we've been trying to do in these sessions, and folks that have been with through the beginning, through all 5, it's really demystifying this acronym, right? I think we are inundated by this acronym right now. You see it, I open up emails, I get emails, STEM this, STEM that, STEM. And I think people are so overwhelmed by STEM. And I think really demystifying it, and this is where your help with your colleagues and the people that you work with, it's literally just an acronym. That's all it is. And I think oftentimes people think it's a binder or it's a box or it's a bunch of stuff that I have to teach, and they really don't conceptualize what STEM is. Somebody, I don't even know who, I'd love to research and find out who, somebody just decided to take these 4 subject areas and, that makes a cute little acronym, STEM. And I remember the first time I went to a STEM thing 10, 12 years ago, I thought it had to do with plants because I figured STEM must have to do with plants. I literally had no idea. And it's literally just those subject areas put together. The glue that holds those subject areas together, again, is this way of thinking. And I think we had that sort of breakthrough moment around session 3. I just saw so many nodding heads and so many light bulbs go off. Remember the bookmark day? We gave bookmarks to everybody, right? And on the bookmark was the engineering design process and the scientific method. And just demystifying that and saying, again, STEM are just 4 subjects that make a cute little word together, but the glue that holds them together is the way of thinking. That way of thinking is the practices of science. And when you order those practices in a certain way, voila, you get the scientific method. If you order them in a different sequence, you get the engineering design process. So that whole notion of practices and processes, and we made that comparison to, you've been doing this for years in your classroom. There's a writing process already. You've been using a process for writing for years. There's practices that you use in reading when you teach reading instruction. So this idea of practices and processes isn't foreign to us. It just seems scary because we're attaching it to some other area of the curriculum that maybe we don't have a lot of knowledge and information about, or we don't have a lot of time to teach. But the more we can integrate this notion of the scientific method, the engineering design process, that is inherently going to help you in all of the subject areas that you teach. So I think if you guys can really become those folks who are like the Tupperware representatives, so to speak, or the Amway representatives, or whatever analogy you want to use, in demystifying STEM for the people you work with and say, hey, STEM is not this big, giant thing. Like the problem of this, how many tennis balls, it's not this big thing. It's literally just a way of thinking. And so the more we can, I think, sell that to people, so to speak, I think people will be more acceptable to hearing the message.
And I think it's important to recognize that it is complex. I mean, this isn't just a question and some data and a conclusion. There's actually, there's parts that fall in between that. And that's why we chose to pull up the KWL model, because a lot of people might say, what do you want to know? Well, that's either my question or my hypothesis. What do I know? They might say it's my research. What do I want to know? They'd either say it's the question or the hypothesis, and what have I learned is the conclusion, and then just sort of wipe out all those things in the middle, but they're actually an important part of the discovery. So we talked about how do we get all that done, so getting to these lesson plans and what we really want to get to here today. Thinking about the efficiency of time on learning. So we just did this crazy activity that we could have done in a 5th grade class, or we could have modified it for a 2nd grade class or a 1st grade class, depending on what level you teach. But we saw that it overlaps math hugely. But if we actually had a nonfiction reading or writing component of that, where we were actually working maybe in a science journal, we actually could have overlapped in all these areas and not had a prototype, but had an experiment. So we would have had science, ELA, and math with all those standards kind of lumped in together with the practices, one activity achieving all of those goals. So that comes to establishing a core of instruction. So today we're talking about identifying resources that support the core of instruction, right? What is the core of instruction? So before we kind of get going on that, what would you say the core of instruction is for whatever grade level you teach? As a teacher, what forms the core of instruction? In fact, maybe that's like a turn and talk.
Yeah, why don't we do that?
Give a minute to
Yeah.
turn and talk.
Person right next to you.
What would you say is the core of instruction?
So a couple of feedback. What did you identify as a core of instruction? A couple of folks. Standards. What else? So she's talking pedagogy, right? We know what pedagogy is. And the opposite of pedagogy is andragogy. Pedagogy is the things you do as a teacher. Andragogy is how people learn. So you talk about pedagogy and andragogy. Standards. What else? Okay. Yeah. Interdisciplinary component of it. Good. A couple others? How about this side of the room? Anyone over here? Understanding? Student understanding? Okay. Good. So
if you kind of walk through it here in a understanding by design model, as well as mixed with practicality, because there's some intermediary steps that are left out of that. Here's a real tight way of establishing a core of instruction that we use, but others do as well. So starting at the grade level, it comes to your standards, right? So a number of people said standards. Now the thing is that sometimes people fall into the trap of this standard. So if you go back to that one activity we did, and you use lists and lists of standards for each grade level, it doesn't mean that we have to do that activity every day for a month. We might have different activities that hit on those same standards, maybe in different groupings. Some groupings overlap, okay? But grouping standards is a first step for that grade level. So take a look at these. These are current mass science standards. So the first one, Earth and Space Science Standard 6, explain how, and see if you can see where this might be going. Explain how air temperature, moisture, wind speed, and direction, and precipitation make up the weather in a particular place and time. Next standard, distinguish among various forms of precipitation, making connections to the weather in a particular place and time. Next standard, differentiate between weather and climate. Next standard, describe how water on Earth cycles in different forms and in different locations, and then including underground in the atmosphere. Next standard, give examples of how the cycling of water both in and out of the atmosphere has an effect on climate. Why are all those standards grouped together?
what ties them all together?
What's tying them together? What's the common thread here? Weather and climate, water cycle.
Water cycle.
Okay. So now we have a group of standards, and this is one of many groups. That's important to put out. This is like planning, you'll see this later on. Scott had a great analogy to this. If you remember planning the tables at your wedding, or if you help someone plan a wedding, you have to consider all these complex relationships, right? You have certain constraints. They don't make tables of 1 and they don't make tables of 50.
Can't happen.
Same thing. These standards are like tables and you're arranging them. But the thing is that it's not just that it's one table, it's the relationship of one table to another. And that's where it becomes even more complex.
Right, because even if you say to yourself, I can't sit, Mary and Frank at the same table, but Mary's at 2 and Frank's at 3, and they turn around and talk to each other, it's kind of like they're at the same table, right? So it's the same thing in terms of the standards and how you group them.
Right. And some people, they don't want to sit up front too close to the music, and other people don't want to be too close to the bar. So on you go. So now that you have that group of standards, now you can start to form units, okay? So, like you said, weather and water cycle, big theme here.
So that's a table, so to speak,
Yeah, exactly.
at the wedding.
So now, like, what's actually going on in there? That unit. Another thing we have to think about is the vocabulary. So just picked up 4 vocab words. Vocabulary is it's words specific to the disciplinary core idea, okay, which in current speak translates into your strand and your standards. So if you kind of trace this back, if we were talking about measuring precipitation as being part of one of the standards, or being able to talk about the weather conditions, or talk about the climate, those are bringing up certain vocabulary words that are unavoidable that students need to be able to know and work with. Okay?
And this is actually, and you know this as elementary educators, the vocabulary associated is huge, huge. The more we can increase the vocabulary of our students, it's going to help in a million different varieties of their learning as they make their way through school. And spending time on the content academic vocabulary as you develop your units and identifying and articulating what that vocabulary is so important, because you're laying the seeds for the unit, so to speak. When you start to teach the vocabulary, you're giving kids the stuff that they need to know later on, right? You do this all the time in reading. You go through a chapter, you pull out the key words, so when the kids get there, hey, there's that word that we talked about earlier when we were doing the pre-activity or whatever the case may be. So that content vocabulary is so crucial to the development of a unit.
Right, and thinking back to the wedding planning analogy, common language, when you refer to climate, if you refer to it by this definition and your neighbor refers to it by a different definition, or next year somebody refers to it by a different definition, think about the student's user experience.
Right.
What actually is the climate? How do I have a clear understanding of what the climate is? Now, again, we're starting to think of resources. We're heading in this direction. Let's say that we go on a field trip, and we go on a field trip to actually, it used to be there in Hamilton, there was one of like 3 stations for observing solar flares in the world. It was a Navy installation. Maybe we got a tour of that place. And they talk about climate by a different definition. So now, again, the students getting multiple different definitions, they're just getting more confused. But if we can have that language in common, so again, thinking about if you're planning trips or you're planning these sort of different lessons, all of it, if it's going to serve your purposes, if it's going to serve your needs best and the students' needs best, all builds up on these fundamentals. So any of these things that change, if you were to change the standards, it would affect the unit. If you change the unit, it affects the vocabulary. Okay, so it has a trickle-down effect.
And a great way to take an x-ray of your classroom or an x-ray of your school district, and the research will tell you this, and it's a great activity to engage in, and it leads to lots of great debate among educators as well. We've been working on this in the district where I work in terms of, we're doing social studies right now. What are the key 25 to 30 vocabulary words associated with your grade level? Identify them. We're having the teachers do this right now. K1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What is the key vocabulary words associated with the units that you teach in social studies? You have to narrow it down to like 25 to 30 of the whole year. And it takes a great x-ray, because when you put them up on the wall and you see pilgrims, 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 it's like, whoa, okay, well, wait a minute. We've got a lot going on with the pilgrims, K to 12, right? So then you have to kind of it leads into these conversations. So it's literally like taking an x-ray of your school system of like social studies, K to 12 in Manchester, Essex. By just identifying 25 to 30 key words, and it takes work, and it takes time, because people are really like, I want the Pilgrims, they're mine, you know. You really have to have those conversations. But in the process of doing that, it's healthy because now, to Francis's point, you're building, and you're identifying what those key words are along the way.
Exactly. And the other thing that's interesting, if you take those key words and you ask people to define them, how would they define them differently?
Correct.
I mean, the classic one is mass and weight. I mean, so many people think that, whatever, it can be either way. And it can't. They're very different. And some people disagree with that, and that's okay. So now kind of continuing on. So we have our vocabulary. Now this is, so when I said that there was little gaps in UBD, and it's not so much that there are gaps, it's just that there are things that get overlooked. Because in the real sense of it, they're all there, but few people bring them in. So usually with UBD, people focus on standards and then assessment and then lesson. But you can see that now the assessment falls out of the unit and vocabulary, right? How are students going to demonstrate learning? Now, this is like a classic sort of question that we might ask, right? Which instrument could have helped students predict that it would rain on Tuesday? Now, the thing that makes a question, I mean, this you could talk a whole day on this, but valuable is if we had gone through and as part of the way that we structure our lesson and questioning, or even vocabulary, if it's, that it's, we go around and basically prompt students all the time and say, hey, what instrument helps predict, the weather on Tuesday or whatnot? What happens is that you end up with students who can't answer the same question asked a different way. So what you really want in an assessment is if we were going through instruction and we were talking about weather, we would be wanting to talk about tools and weather prediction, and then we ask a question that requires them to apply that in a new context. And in this case, students wondering if it would rain on Tuesday. Okay, that's a context, not necessarily something that was part of a lesson. So this is where the resources, activities, and tasks come in. So I put a little picture of a mini weather station in there. So many people will just build something, and it's like, okay, so we built it, but if we know what we want to assess, and if what we want to assess is what tools are used to predict the weather, building a little weather station doesn't necessarily give a student the opportunity to interact with that and internalize the concepts of weather prediction, how weather tools function, what the differences are between the weather tools. So while this is, potentially a resource activity or task, depending on how that came about, it's only really useful if it gives us something that feeds the assessment. So that's why I put it in italics and out here in the brackets, because it sort of sits on the side. What's going to determine it is how the students will apply and internalize the standard. So if you take a look here. So if we take that little weather station that we built, and then we go along and we actually observe the weather using the weather station, and maybe we use the weather report. So now we take the weather station that we created, and we know what each weather instrument is, how it's supposed to function. We record data with it, and then we compare that data to weather data from an actual weather station, maybe on the news or in our school. A lot of schools have little mini weather stations someplace. Weather bug, who cares, wherever it comes from. And begin to look and sort of compare and contrast. So now we're coming back to those higher order thinking skills of how and why were my observations different than the weather station in our school or on TV. I mean, and it kind of comes back to that tennis ball example of, does it really matter that your your anemometer estimations were off? Not so much, but it matters that you recognize that they were off, and you recognize some of the contributing factors as to why they were off. And so that's giving the student the opportunity to interact and internalize those concepts. If we had just stopped at creating that model, we would have done something fun, and students probably would understand the vocabulary. They might be able to apply the vocabulary to a picture of an instrument, but you wouldn't be able to get that higher level thinking, the analysis, the evaluation, and the creativity. So now we could go back, and let's say we went through the weather station log, and we had collected that information. Maybe we go back and talk about now let's tie it into engineering. How would we re-engineer the instruments? What would we change? Okay, maybe the barometer, maybe we used a balloon with the barometer, and that reacts with some things in the air. We notice little holes start to appear after so many days or months or weeks, depends on how long you were doing this. Could we use a different material for that membrane? Okay, maybe there's friction. Maybe we notice that there's some kind of contact between the anemometer rotor and what it's sitting on. Maybe there's a way to reduce the friction or make less drag.
And this is it's time bound, right? I mean, you think about your day, you think about how much time you have, and a bizarre analogy just popped into my head, and it's got to do with wine. I don't know why it came into my head, but it's a continuum, right? And at one end of the continuum, it's the person who buys a bottle of wine because they like how the label looks, right? And then at the other end of the continuum is the person who owns the vineyard and knows what kind of grapes it takes to actually make the wine, okay? And all along that continuum, and I think at schooling it's the same way. It's when you think about the work that you do with the kids, when you think about the resources, activities, tasks, the vocabulary, the assessments, you have to figure out in the amount of time that you have, if you live down this end of the continuum, there's probably not a lot of learning going on, right? If you live down that end of the continuum, there's a ton of learning going on, but that's probably 6 hours a day of science, right? If you own the vineyard and you know the grapes and so on and so forth. So we've got to figure out that balance between where are we on this continuum in terms of, yeah, we need kids to internalize, where was that word that you had up there? Internalize and make sure that they can think at a higher level, right? So this is lower order thinking down here. I like the label on the wine bottle. This is higher order thinking up this end. I own a vineyard and I can tell you the composition of the grapes and when I do all the things to make the wine, right? And so somewhere in the middle is some sort of a good balance because it's certainly time-bound as well. And we're aware of that. Know that when we talk to you about these things, we know that you are time-bound. We know that if we asked right now, how many of you regularly teach science? We're not going to do that. It'd be very, very different because of all the other demands that you have going. So that is why when we talk about thinking and we talk about establishing that core of instruction and grouping and tightly coupling everything, the more you can tightly couple everything in your classroom, the more efficiencies you can find, the more time you create to put yourself further and further down that continuum.
And if you think about that standards grouping, that's why it's so important. Because if you can group your standards and you can do lots of standards together, and actually, and I'm not holding up the model units from Common Core stuff that the DESE has published as being perfect by any means, but one of the things they're trying to do in there when you look at the ELA lessons or the math lessons, they're trying to show how standards combine ELA with social studies or with science to get people thinking about how they're grouping standards. Because if you group those standards like we were talking about, if you look at that activity, we could very easily involve math standards, science standards, and even ELA standards, and actually in a little bit we'll look at social studies standards that could relate to this, related to pilgrims, believe it or not. So that's how you go from the 6 hours back down to something that you can accomplish.
That's meaningful.
That's meaningful. And the thing that's the challenge is, and Scott had a good term for this, when we're used to doing something that works, so we keep doing it.
Yeah, competency traps.
Competency traps. We're so good at pull out one standard and do it. Pull out another standard and do it. The problem is there's too many standards to do it that way. So if you think of that big group of standards we started with, all around weather, water, climate, if you pull those out individually and go through this whole process and create all individual tasks, you do that all year. But if you group them together and you do one task that accomplishes multiple standards, you get a lot of opportunity to do higher order thinking and learning, and make good use of that time. So that comes to, I'm sorry.
Well, I was just going to say, and Patty, where are you? Patty's right there. So Patty and I had the conversation earlier. This comes back to, what do you need to do this? Time to what? What's the word? Plan. Who just said it?
Yeah, time to plan.
Plan. It takes time to plan. And in the current environment that we're in, right, with all eval, DDM, essential questions, do this, do that, do this, do that. Maintenance, right? Maintenance on your units. Think of it like a car, preventive maintenance. How many of you are using teacher-created materials for your science instruction? You don't really have a program. You're winging it and you're pulling stuff together and you're doing the best you can with what you got and you're starting with what you have. Yeah, right? That takes maintenance and time to plan and to pull together and to do those things. So know that we know that. Because I know if I was sitting out there as a teacher, I'd be like, sounds great, but it takes planning time to do that. We're aware of that, okay? And part of the conversations that we're having as a part of this whole programming is with the administrative staff in saying that this is important. This is a value. And I can tell you that more and more and more and more people that we talk to are seeing, yes, this is important. This is a value. We need to make sure that you have that time to maintain what you have, to work on what you have, and to bring it to a point where kids are able to internalize the information that you want to give them. So know that we're not tone deaf to that this takes the time to do that, and we're working with folks to stress that message that, yes, we need to get that time back to you in order for you to do that.
It takes years and hours and hours and hours. I mean, that's the reality of it. And the reality for teachers is that a lot of what should be coming to you is pretty much everything here. Because you could put your whole classroom aside and do this full time for a decade and just be kind of arriving at something that's fairly solid at that point. Because when you think about those unit groupings and standard groupings, units, and vocabulary and all of that, you need to be on the same page with your peers in a lot of those pieces, because you're going to be handing these students off to somebody else next year who needs to understand where these kids have been, what they've done. But also, if you're in a big district, kids move around. So if they go from your class to your class to your class, this is trick because they're chasing rent or something like that, and they can potentially end up doing the same unit all year long by virtue of the way that it happens.
Right.
Okay?
And so I just think the other important part of that, the rest of that story, right, the Paul Harvey rest of that story, what I just said is, but you have to start somewhere, right? You can't look at it and go, like when I had that initial reaction of how many tennis balls will fit, oh my God, I can't figure it out. No, you have to start somewhere. It's like exercise, right? I look and I go, oh, there's the treadmill again collecting dust, right? If I do 5 minutes today, 5 minutes, and 6 minutes tomorrow, and 7 minutes the next day, and 8 minutes the next day, I will have made an impact. So if you do this for one unit, for one area, and you have to start somewhere, and if you just start small and you start to make those changes, you'll see that you kind of get into a rhythm and a routine.
Great. Okay, so this here, I want to ask you, where does this video belong in a lesson? So we're going to show you this video. It's a selection from NBC.
STEM of the Olympics is NBC's got a whole thing out right now about the STEM of the Olympics.
Okay, which looks like this. Okay, a bunch of different videos on here, skiing, half pipe, all this great stuff. And the video I'd like to show you is the one related to snow. And I want you to be thinking, where does this belong in your lesson? Because I can tell people are already excited. I want you to be thinking about where would you put this in your lesson, and hopefully I can maximize it.
It's the hard-packed launching pad for snowboarders, the slick racing track of cross-country athletes, and the speedy slope for downhill skiers.
The snow conditions are huge. Some races you'll have really icing conditions, some races are soft.
Snow is an essential part of the 2014 Olympic Winter Games. In fact, organizers in Sochi are worried whether or not they'll have enough of it. The science of snow, how it's formed and how it reacts. has been studied by scientists for centuries and continues to this day.
Snow is the crystallized form, the solid form of water, but that is formed in the atmosphere so that it is able to take on a unique crystal structure.
Sarah Conrad is a glaciologist at the University of Wyoming, but unlike many of her colleagues, she's also a former Winter Olympian.
I competed in the 2006 Olympics in Torino, Italy, and I competed in biathlon and in cross-country skiing.
Snow is a form of precipitation that begins as tiny liquid water droplets in the clouds. In order to turn into snowflakes, these water droplets need to be what scientists refer to as supercooled.
You're right on that point of going from liquid to solid. We have a freezing temperature for water, but that freezing temperature can change based on your altitude.
Supercooled water remains in liquid form, even though it's below freezing temperature. For it to freeze, it needs to come in contact with other particles like dust. These particles provide the impetus to start the freezing process.
To make that transition, which takes energy to go from water to ice, it needs something to start it. It needs a nucleating particle. So a piece of dust, a piece of random gases, a lot of emissions from smokestack, different things like that. When the water hits that particle, it can begin to freeze and form a crystal structure.
Conrad demonstrates this process using a bottle of supercooled water, pure distilled liquid water that is below freezing temperature.
It's pure distilled water, so it doesn't have any particles in it.
Disturb it with a few good smacks, and instant ice crystals.
See the ice slush up at the top?
The ice crystals that form in the clouds become snowflakes.
As they accrete and freeze, they'll grow outwards in that pattern.
Snowflakes come in many different shapes and sizes, but can be grouped into two categories: plates and columns.
The kind of stereotypical snowflake that we're used to, those beautiful six-fold symmetric crystals, those are called dendrites, and that's a type of plate.
Court Anastasio is a chemistry professor at the University of California, Davis, and funded by the National Science Foundation. He says that the size and shape of snowflakes is determined by two important variables: humidity and temperature.
Dendrites form under conditions where you have a lot of water vapor. If you have less water vapor, you get much simpler shapes, like small plates, small columns.
Once the snowflakes land on the ground, physical changes begin to occur almost immediately.
It gets blown around by wind, can be broken up into smaller pieces. The snow crystal shape changes.
The crystals start becoming rounder and smaller. And once they're round, they're more like ball bearings. And at that point, then you can ski across them much more quickly.
Sometimes there are those courses or those snow conditions where you're just like,
In Sochi, after 2 mild winters, organizers have made contingency plans that include storing about 588,000 cubic yards of snow under insulating blankets in nearby mountains. But experts worry that stored snow can't quite compete with freshly fallen powder.
It's going to melt, and then when it gets cold again, it's going to refreeze. And so it's going to be really icy.
Though tiny, soft, and delicate, when snowflakes accumulate to form blankets of several feet, snow becomes the ultimate playing surface upon which Olympic dreams are made.
I learned that I'm never going to eat snow again now that I know that it attaches to pollution. That's good to know. Dust, and yeah, I think I'll pass on that.
So should we turn and talk, or just, what do you think?
Yeah.
Let's give one
Actually,
minute.
Go ahead, sorry.
I was just going to say 1 minute turn and talk.
Yeah, actually,
Where
why
does
don't
this belong?
you just stand, turn and talk to give yourself a little stretch break as well. So stand, turn and talk. Where do you put this? Beginning, middle, end of a unit.
Okay, how about a little feedback? So where does it belong? What you found this resource on the internet? It's cool. What do you do with it? Where do you put this as part of? Because in some ways, if you're acting in a resource capacity or library capacity, or you're trying to plan an activity off-site, You have to kind of ask yourself these questions all the time. So where does it belong in the lesson? What do you think? Anybody want to share? Where does it belong in the lesson?
Go ahead.
Pete, so I agree. So I think that would fit, well with all of what you're saying. The place I go is two places. One, in terms of its value, go back to the practices. Where is the student, through this video, how is the student engaging in these practices? Are they asking a question or defining a problem? Are they developing or using a model? Are they planning or carrying out an investigation? Are they analyzing or interpreting data? Depending on the data that's there, you might say, you might make a case for that, analyzing, interpreting data. But are they using mathematics and computational thinking? Are they constructing an explanation or designing a solution? Are they engaging in argument from evidence? Probably not. Are they obtaining, evaluating, communicating information? Maybe. So when it comes to its place, does it become a core of what you're doing versus that sort of entrance activity or an activator, or maybe some kind of a part of a summarizing activity? Or does it become part of an assessment? Because if you've just done an entire unit, this is a completely new context, isn't it? So you could actually take that video and make it part of an assessment. If we've just done a weather and water unit, water cycle, we could now ask the students to analyze, evaluate, or create using what they know as it relates to what they've seen in this video. So
you're saying it shouldn't be the core of instruction, but it can be a tool to use as part of the core of instruction.
Yes, but see, the thing is that when you come back to the discussion about vocabulary and language, remember how vocabulary is part of setting up your lessons? The hard thing about a video like that is that the vocabulary is all over the place, right? There's a lot of things that, to a second grader, nucleating particles. Okay. Maybe you got that kind of class. Most people don't. But there's other things there that would be interesting. The thing, though, is that even in terms of a snowflake, they call it a dendrite.
Right.
Well, okay, now you're going to need to make that connection between your snowflake and the dendrite. And that's great. Sure, that's great. But most people, now the thing is when you come back to those vocab choices, when you're choosing that the vocabulary in your lesson, that your lesson will then reflect, you have to think about, it's almost like you have to pick and, this is where we were talking about the pick and choose.
Yeah.
When it comes to the snowflakes, if you're doing a unit around snowflakes, I guess, what would be more core? Like the states of matter, the basic geometry maybe, or the dendrite? Where, how would you rank? And then if you had to choose your top 10, would dendrite actually end up on that vocabulary that's disciplinary core vocabulary? Probably not. Even though it's stuff that students could learn and might be a great enrichment piece or an add-on, it's just, again, back to that core of instruction. This is what I'm trying to articulate for you is that there's a bit of a sorting process that goes on here. So there's lots and lots of great resources, but as you're sorting them, you have to be thinking this way because it's stemming from the standards, and you want your activities and your resources to continually reinforce that core vocabulary, the core standards, and the core activities. So a couple common issues to keep in mind, too, with STEM lessons. One, seeing is not doing. The new science standards, the draft standards, and you have copies in your bags, we're not going to get into all the nuances in the new standards. There's actually, we're holding 2 webinars this week. We're going to hold it tomorrow anyways, but if you're interested, that's all talking specifically about the new mass STEM standards draft that's coming up for adoption. But just to sort of give you a really quick peek, seeing's not doing. Okay, the new standards more than ever are going to require students to be able to do. That's exactly how they frame it. Okay? A standard is what a student should be able to do. Participation is not ownership. So seeing is not doing. So again, you think about the textbook, you think about the videos, they're all pieces of the puzzle, but students need to be able to internalize, need to be able to do. Participation is not ownership. So if you think about back to your teams today, trying to figure out how many tennis balls fit in this room. In your group, it naturally happens as part of group behavior. You probably had some people who were process owners. They were maybe calculating the volume of, or measuring the length of, or something related to that. They had ownership over it. Other people may have participated in the group, give some ideas, but they didn't own necessarily parts of the process. So now if I pull them out of your group, and I say, you know what, you guys, you got within 100,000. I know the rest of your group went home, but what I'd like you to do is I'd like you just to repeat that for everybody up here. Okay? While they participated, they didn't necessarily have ownership, and they didn't internalize how that all happened. So their ability to then do it is severely mitigated. Okay? So that's really important. We always talk about learning to read and then reading to learn, right? But what's really important is that in STEM classrooms, a lot of times people get stuck in reading to recall. Okay? When you think about Bloom's taxonomy and those lower order understanding up to applying, you can read and get through a lot of that, but that does not necessarily make you competent to be able to do or own what's going on. So instead of reading for understanding, it's important that students are in a position to practice. So just like in your group, you were practicing, took the tennis ball, and I saw people coming over here and going, okay, let's see, 1, 2, 3, they're actually doing that. Running into the problems of trying to measure a straight line with a tennis ball. Okay, that's important because those are the things that are going to bring those STEM practices into focus and internalize them. The other thing is practice without purpose. So the new standards talks about, it makes a case for grade-by-grade progressions. This is the state's sort of attempt at making people think about grouping standards. Okay? They're saying, standards are not curriculum. But you need to think about grouping them and you need to think about ordering them not only within the year, but from year to year, because what's happening as students move along is important, and this is solving problems for them because if you can imagine, like I said about Newark, New Jersey, students moving around from one district to the next or within a district, traditionally people have not thought that way. Practicing without purpose comes in when we know that we have certain standards we're trying to work with and we're just sort of trying to punch it out. If the standard is being able to differentiate sedimentary, igneous, and metamorphic rocks, we can pick out our 3 sedimentary, igneous, and metamorphic rocks and put them down in front of the kids and say, okay, which one's the sedimentary, which one's the igneous, which one's the metamorphic, and they'll be able to do that over and over again. But if I change those 3 rocks or make them a different shape or a different color, how many of them have internalized the characteristics of what makes something sedimentary, igneous, or metamorphic? And the only way that you really get that to stick is, again, back to that wedding planning, right? It's how you seat those concepts around each other, how you group them. So back to that little goofy weather station, that's a useless activity if it's not connected into weather, water cycle, climate, even states of matter, and then life cycle. Another place you see this come up is when, we all like to do life science in the spring, right? Set all our butterflies free because it's springtime. And we do that right after we do electricity because electricity and life science have so much in common, right? it's feasible. It's more feasible that way, but it's not for learning purposes. That doesn't create synergies. And it actually, by considering how things are ordered, you can create more purpose and more connection, and that, again, helps students internalize things. I could go on about that one for a while, but so anyway, are there any questions on these? I thought I saw a hand. No?
So it's purposeful and tightly coupled, I think, are the messages, and meaningful.
And you can always tell that because when you ask a student, why are we doing this? What are we doing? And they say, because we're making this.
And that's the thing. Confusion will build on confusion, right? I mean, that's so important, too. I remember one time, different district than where I work now, but I walked into a science classroom, and I said to the kids, I like to go up to the kids and ask them, how's it going? What are you learning, right? And I walked up to a student, and she said to me, I said, hey, how's it going? This is high school. And she said, I'm very confused. She said, but the good news is we're all confused. So because we're all confused, we feel like we'll all get through this, right? And I walked out of there like, oh my God, right? So there was mass confusion, but there was comfort in mass confusion because she wasn't the only one who was confused, right? So clearly there was a user error there somewhere along the line that we had to help the teacher clarify what it is so that he was trying to teach and so on and so forth. So when you build misconception upon misconception, that's not good, right? And so having meaningful instruction that kids can understand, and it all starts with that content vocabulary and building upon the vocabulary and grouping the standards. And I think you're seeing how this all, and I think this is all stuff you know. It's just stuff you need to be reminded of because there's so many other things that have our attention. And if we can come back to the base, and we know what the base is, and we know how students learn, and we know what we need to do to teach to get kids to learn, that's how it all comes together. And
I guess I kind of picture it like if you drive a 5-speed or like a manual car, or have ever attempted it, it's strange, and the ordering of the gears matters. If you go from one to the other in the wrong, you could just your car stalls, it hops through an intersection, you get pulled over, all these bad things can happen, but yet and the thing is that the gears are not necessarily in proximity to each other like 1, 2, 3, 4, 5, like in a row. They are up and down and over and reverses, like up in the corner or down in the corner. When you're ordering units because of butterflies in the spring and electricity in the fall and things like that, what you're doing is you're jumping around. You're jumping around in ways that cause you hopping through intersections. And from a student's perspective, again, they're the ones who are trying to make sense out of this ultimately. They're not going to make that connection. So it either puts it on you to somehow connect electricity to life science and, look at the grow light uses electricity. Well, that's not that's ketchup is a vegetable, okay? But the smoother transition is much more important because it creates a narrative. And that's the big focus of the new standards, creating narratives. We talk about essential questions, right? Creating a narrative is along those lines. Smooth transition all the way along.
All right, just to kind of recenter us a little bit and come back with this whole idea of thinking. Paul, a gentleman from North Reading who attended a bunch of the sessions, was talking with Francis and I right before we went out to lunch, go to lunch. And he was reiterating the importance of what he tries to do in his classroom, which is helping kids to understand the thinking, right? It's all in the thinking and understand why kids are thinking a certain way. And when he said that, it prompted me to think of a gentleman by the name, and I want you to write this name down. His name is John Hattie, Hattie. Hattie, yeah, John Hattie. And John Hattie, in 2009, what they considered to be sort of a milestone of educational research, he went out and did a meta-analysis, a meta-analysis, really. And you can see there up on the screen, Hattie's book is designed as a meta-analysis study that collects, compares, and the analyses, the findings of many previous studies in education. So he took, I think it was close to 50,000. If you can scroll down a little bit, Francis, please. Yeah, right there. Yeah, well, visible learning is nothing less than a synthesis of more than 50,000 studies covering more than 8 million pupils. Hattie uses a statistical measure of effect size to compare the impact of many influences on student achievement, class size, holidays, feedback, so on and so forth. So he looked at student achievement, and he looked at all these things over here that can affect student achievement. Now, you don't need to know all the data and all the background and all the blah, 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 blah. What you need to know is his magic number was 0.40, and I'll explain that in a minute. If you can flip to that other slide there. Yeah. So on this slide, if you can scroll down a little bit. Keep going, keep going, keep going. Is there a way to make that full screen?
Yep.
Great. Now scroll up a little bit, please. All right. So this chart right here, how do we know what has the most impact? You may not be able to read that, but basically, in his study that he did, anything greater than 0.40, okay, that was where student learning accelerates. Anything at 0.40, student learning is a year's worth of academic. 0, no effect. Less than 0, student learning is negatively affected, okay? So, pretty obvious ones. Student learning is negatively affected by retention, summer vacation, television. Interestingly enough, as you read this, though, look what's down the bottom here. Teachers' subject matter knowledge. We always feel like we have to know every single thing that we need to know in order for the kids to understand it. Look at all these other things down the bottom. Ability grouping, mentoring, class size, summer school, homework, inquiry-based teaching, all less than that magic 40 number. And there were some surprises on there when I first looked at it. You look above the line, things that have an impact on student learning, and where student learning actually accelerates. Cooperative learning, some solid writing programs, questioning, parental involvement, obviously, peer tutoring, direct instruction, metacognitive strategies. Metacognitive is knowing how you work as a person. Feedback, right? Feedback to you. Acceleration, formative teacher evaluation. Formative meaning along the way we work together and we help and we give ideas and we share ideas. And then the biggest one, by far, 1.44 being the factor there, student visible learning. And what Hattie describes as student visible learning is seeing learning through the eyes of your students, okay? And the way that you see learning through the eyes of your students is you find out how they're thinking. What was their thought pathway that got them to the answer? That's the biggest effect on accelerated learning, accelerating learning for students in your classroom. And the reason for that, and this is part of the conversation we had right before lunch, you don't see it. Kids get to some conclusion, and you're not there for the ride in their head along the way. Wouldn't it be great if you could kind of climb in and see exactly what they were doing? So the more that we can make that visible, we can figure out like where kids are falling off the ledge, so to speak. So if they're taking a road to the top of the mountain, that's kind of a scary one over here on the ledge, right? You need to know that. If they're taking the safe route to the top of the mountain of knowledge, you need to know that. If they're about to fall off, you can fix that. And it got me even thinking even more after our conversation ended. Student visible learning and looking through the eyes of the child, it becomes even easier to manage if you follow this idea that we've been trying to talk about here, which is using practices and processes. If we can instill those, if you build it in the architecture of your kids, you now know how they'll be thinking because you have built it into your subjects, the core concepts that you're trying to teach. So if we can get kids to think in this way that we want them to think, that we know will help move the needle in education, you no longer have to be as worried about how they're thinking, and you can focus more on the other things that you need to focus on. Because right now, kids are thinking like, right now, all of your brains, I'm not in all of your brains right now. And the connections that you're making to this, I see some people taking pictures of the chart, some people writing stuff down, and you're making various different connections to it. I'd love to be inside of all your brains to think of what's the voice in your head saying to you right now. Hurry up, Scott, get to 2:30, maybe. But you're probably making some sort of a connection. There's something up there that probably surprises you. If I was sitting in the audience, I'd be like, really? That's that low? I need to look this up when I get home. I'd be doing that. Because you all bring your different experiences and everything you've learned up into your life at this point to this map, of the graph that's behind me. So this whole notion of student visible learning, I think, really ties up with a nice bow the 5 sessions, so to speak, of like what we've been trying to say is that it's all about the thinking. And anytime we deny kids an opportunity to participate in a STEM subject, you're denying them an opportunity to think in a way that's going to help them. Okay? Content becomes the vehicle, as we said, to practice the thinking that we need kids to do in order to achieve at higher levels. Higher order thinking, problem solving, problem identification. We know that those are the types of skills that we need our kids to be able to do. Analyze, synthesize, evaluate. And the more we can build into that, the better served we'll be. So
I just wanted to see if I could pull up, which I'm not going to be able to do it quickly. That chart is actually a subset of a much larger one.
yes.
Basically, like all these things go. He did the study, wrote a book, licensed the concept to a company which now produces
Right.
whatever. And so that chart that you saw is a subset of information from the study he did around...
And Cohen bought it. Cohen is a big publisher.
Yeah.
They bought it. He wrote a book. And now there's like an entire professional development series about student visible learning, basically.
yeah.
But if you just Google student
Here's-
visible learning or John Hattie or Cohen student visible learning,
But
you'll
there's-
see all of this information.
Yeah, I'd say there's probably 4 or 5 times as many
Items on the list.
items on the list.
Yeah.
So,
Yep.
so it's something interesting to look at, and the ranking.
But the pull away is the thinking. That's the pull away. That's the message. We need to get our kids to think in this way that they're using the practices of science and engineering and putting them into a process.
Absolutely. So
Paul, thank you for prompting that discussion.
moving in that direction, just recapping. So, where did the lessons? So the lessons that you hold, that you brought with you, or that you're going to connect with somebody around you about, they should originate from assessments, vocabulary units, standards, and your grade level. Hopefully that came to you from your district, from your curriculum director, or something like that. Don't feel bad if they didn't, because most people are in a situation where they create their lessons, and that's kind of all up to them. But hopefully that's not the case. Doing it yourself, the first thing we've got to think about, and we've kind of already talked about this in one of the earlier sessions, kind of using this UBD model, so understanding by design, or sometimes people talk about backward design model. Identifying the desired results. So that lesson plan you have in front of you, you need to ask yourself the question, what are the standards? Okay? So if you brought an activity with you, what are the standards behind it? Why does it exist? Okay? Just like think back to that movie. If I came into somebody's classroom and I sat down and I saw that movie, I'd say, why does this exist in here? What place does it have? And that all comes from those standards, right? Next thing is, what are the practices and processes? So we've been talking about that. That's all those 8 practices. The processes are whether it's a scientific process or an engineering process. And we've been talking about those. Now, the third thing is, what are the disciplinary core ideas that relate to these? Disciplinary core ideas are the concepts related to the standards, and they're really defined by the strands. So the strands are things like earth science that break down into broad topics like rocks and minerals, water cycle, things like that are kind of more broad topics. The disciplinary core ideas, that's a fairly new term. That's what's coming from these next generation science standards and the new mass standards, okay? So the lesson you're holding in front of you might be a social studies lesson. So what are the standards for social studies? Maybe that is a social studies and an ELA lesson kind of combined. What are the standards there? How can we add some element of science, technology, and engineering standards to it? So the thing is, in STEMifying that lesson, it doesn't mean that you are necessarily going to get a full science standard in there. A lot of times you can. It depends on the context, okay? But it might mean that you're incorporating STEM practices and processes. So earlier in the series, we had talked about this idea of asking the question in social studies, why did the Pilgrims move on from Provincetown? They landed there first. Seems like anywhere you land would be good after that voyage, right? But we can use STEM practices to help answer that question, okay? And in that process of trying to answer that question using STEM practices, we can actually bring in disciplinary core ideas. Things about climate, weather, water, okay? The difference between weather and climate. Depending on how we structured the activities, I mean, we could also bring into it climate change, okay? Looking back maybe 100 years, I know the Pilgrims were well before that, but 100 years ago, just to see what has the change been in the last 100 years, okay? So identifying the desired result. Because oftentimes what happens to us, and this is the reason I'm trying to linger on this and be really as concrete as I can, and please ask questions if I'm not being clear enough. Oftentimes what happens is I used this activity today, and it went well, and everybody did it, and everybody smiled, and everybody left happy, and I'm going to do it again, right? And then what happens is over time, either the standards change or something changes related to it, or there's a better way of accomplishing that same goal, but you know what? I still do this. And that's very understandable. But the thing is that this is how you kind of innovate as you go along and pull these ideas together so that it's, you know, if I could have done this with something other than tennis balls that maybe brought in another dimension, it would be worthwhile to make that change. So the result is not, this tennis ball thing, the tennis balls are not the result, as I guess. So we really need to think of why we did this. And if it was done in a classroom, the reason we did that was those math standards and those STEM practices, okay? And also the pedagogy of being able to get the students to internalize by doing, using all of those standards and practices, okay? That's the desired result, not the number of tennis balls that are in the room. So the next piece is determining the evidence. So how are you going to assess that? So a couple of things to keep in mind. You're going to assess it because you need the students to be able to demonstrate it. Demonstrate it means that the students will be able to do the standard. They'll be able to demonstrate the standard. On the left here, you have the 6 facets of understanding, okay, from UBD. And then over here, you have our sort of rearticulation of Bloom's taxonomy and higher order thinking. So again, thinking back to the standards and the purpose that it exists, right? It has a purpose. How are you going to assess that? Are you going to be looking for students to interpret something based on the knowledge that they have, what they've learned? Are you going to be looking for them to be making applications, explain? Are you going to be looking for other things? Things like shifts in perspective, self-assessment, empathy. So a conclusion, in some ways, when you look at a scientific, going through answering a question scientifically, that's a kind of a self-assessment. It's an assessment of the process, the way you've used the practices, and that you have articulated this process, and you've come and gathered some data, and now you're reflecting back on it, okay? Shift of perspective, that's pretty straightforward. Interpreting and applying, unfortunately, most of what we see most times is the bottom 2 there, either explaining or applying. So if you can explain it or you can apply it, that's good enough. But the thing is that's not the only dimension here that we're trying to look at. And those explain and apply are really living in the lower order thinking, and that's why this other chart is up here. It's remembering, understanding, applying, but it's not necessarily creating, evaluating, or analyzing, and that's what's important. Those are the sort of things that give us these shifts of perspective and give us those sort of discussions where, and I won't put Priscilla on the spot, but she had shared about a student who had a shift of perspective in terms of what she could do to help people using her knowledge of science. And I think, I know looking at some of the feedback from folks here, folks have articulated shifts in perspectives, even about things like what a scientist or an engineer is. So a shift in perspective, you look back to that video that we saw about the skier, right? It's a little bit of a shift in perspective. It's not just about weathermen on TV talking about the snowpocalypse, right? It's about actually using the science and the technology to be able to enable people to compete in the Olympics. What is the value of the Olympics? Why do we have it? And how does our ability to use science to store snow, create it, and create these competitions actually shape our community? Okay, so those are different opportunities, like different elements of being able to access and give students opportunity to demonstrate the learning. The other piece of it is what is the acceptable performance level for success? And I think Scott, we've talked about this in terms of time plays a big factor.
That's a time-bound question.
Exactly. Oftentimes, like the less time you have, what's acceptable for performance sometimes is compromised, right? When you think about even the activity we did today, I'm sure when you started to see how other people were attacking it, maybe it created a shift in perspective of how you would attack the problem. But people were probably using different practices or different models than you were using. And what's important is that we're not always setting the bar. I guess the thing is that you can set the bar at a level where you try to get everybody across this bar, right? We always want mastery of everything. And mastery is important. But the thing is that focusing on what you're trying to master and what you're trying to introduce and what you're trying to expose the students to, those are sort of like different shades of gray. And it's important that, we're not, in the case of the tennis balls, whether you remember how many tennis balls fill this room or not, that's not something to be mastered. Who cares? But what I really care about is that you've had exposure to those processes, actually using them and doing them. And if you can master those, and maybe the way to master them is incrementally, right? And trying them and doing them, you have multiple levels of performance for different aspects.
Well, and I think, Rick Lavoie uses the phrase successive approximation, right? And successive approximation is a fancy way of saying celebrate direction, not perfection, right? And when you celebrate direction as opposed to perfection, if you're always waiting for perfection, you're waiting for the end result, you might not know if the process to get there is working or not. If you celebrate direction and growth along the way, you have a better chance of having an understanding of whether the performance level at the end, this idea of acceptance, what is the acceptable performance level for success, that becomes an easier thing to define if you have kind of walked with the child along the way and followed his line of thinking again, as opposed to waiting until the very end to see what the end result is in terms of the child's knowledge.
Exactly. It's sort of like the principle of riding a bike. The principle of riding a bike is you can talk about it, you can see the video, you can do whatever, but you get to get on and ride it. And you might need some training wheels to start with. And so you go, and then you have to, at some point, take the training wheels off, and sometimes you fall. But the thing is that you're incrementally working towards a goal, which is a performance level of not falling off, right? Be able to, whatever, Tour de France.
I'll take that one step further because it just put something in my head. Driving a car. When kids are 16, we don't throw them the keys and say, good luck, pal. Go to it. I know you can do it, right? We go through a process where there's someone actually in the car with them, and what does that person in the passenger seat actually have on his side or her side? The brakes, He's got a set of brakes, or she's got a set of brakes on his or her side. Teaching's a lot the same way. You can give him the steering wheel, but if he starts to go down the wrong path, you press the brakes. And you kind of pull the wheel back over here and you say, let's go. And so there's a gradual release of independence in that model, right? That whole driving the school model, it's the same thing in terms of what we're trying to accomplish here.
Exactly. And that's all valuable learning because it's the opportunity to get it wrong in some cases. So stage 3. So now that you've sort of, you've defined what sort of evidence you're looking for, what you're going to be assessing, you know your standards and all of that. Now you actually come down to planning the learning experience and the instruction. So, kind of thinking about that waterfall, you're down to that lesson at the end. These are the questions you need to be asking yourself. What's the narrative that connects the activities to each other? And that includes the sequence of activities you're doing. So that little weather station activity, if that exists in isolation, it's got very little value. So what did you do? What is the activities that come before and come after that? And the thing is they may not necessarily be that same group of standards. Again, back to that idea that if we always do butterflies in the spring and electricity right before, there's no synergy between those two. It's not a clear synergy. Okay? But if you do something like you talk about the water cycle, and then you talk about weather, and then you talk about climate, and then you talk about things like life cycles, you can see there's a clear thread there, right? Because you can go from states of matter to weather and water cycle. The water cycle allows life on Earth, right? And actually is part of what creates the climate that's unique to different regions that allow for unique adaptations and for the unique life that exists there. And then you can look at that in terms of what are the life cycles of these species of organisms? How do they reproduce? How do they exist within food chains and food webs? Okay, and that continues on and on and on all the way through, carrying the concept of energy forward, food chains and food webs. Now you actually start to have a tie into things like electricity, right? Because electricity is a form of energy. Where did it come from? It wasn't just created, right? It can't be destroyed. So that's why this idea of a narrative is very important, because it connects the units, it connects the standards, it has a specific sequence because, again, it's a narrative. You wouldn't read books out of order. And it helps you to order your activities to create purpose and synergies between them.
And I would say the reality, I think, for a lot of folks in schools is that the sequencing is often determined by who's got the materials, right? I think if you're in a big school, it's like, there's 10 fifth grades, let's say, in the district, and there's not enough material, so the material is just kind of, I'll do this now because I'll have the materials and you'll do it, and then we'll kind of rotate and we'll switch and so on and so forth. So again, with that whole idea of starting small, right, exercise 5 minutes and then 6 minutes and 7 minutes, that's a great sort of entry point into looking at, pull that out and say, why do we do it this way? We've always done it this way because we have to share materials. Well, if we have to share materials, just very simply reorder in a way so the narrative has a sequence to it, a purposeful sequence to it.
Exactly. So then within that, whatever that part of the narrative is, it's what's the multidimensional task? So the thing is are you looking at sedimentary, igneous, and metamorphic rocks simply to look at them and say, this is sedimentary, this is an igneous, this is metamorphic? Or is it multidimensional? Are you doing something with sedimentary, igneous, and metamorphic rocks? And actually, even better, like I think earlier on we had talked about things like countertops or curbstones or different elements of the building materials that make up the building that we go to school in. Okay, if we can start to relate those, we can start to make social studies connections. Why would we find a lot of granite here in the Northeast and not in the Southwest? Why would we choose that material for a curbstone versus this other material? Why that type of rock? So if you have the right task or activity that comes together, you can ask these sort of questions instead of just simply, is that sedimentary or igneous or metamorphic identification? How do the activities challenge the students independently and as a community? So if you think back to the activity we did earlier today, in some way it gets to this point. It challenges you independently to contribute to the group, but it challenged your group as a community because you had to come together and agree. You had to use the skills, you had to pool your ideas, and you had to come to some conclusions and actually be able to come to some answer as a community, even if it's 2 or 3 or 5 people. Oftentimes we see this goes into sort of 2 spectrums. It's either that the focus on having an answer that's, okay, I know if I got this, it's right, because they are equal. So it becomes sort of an individual challenge to get something right. Or it becomes so community-oriented that it's really more around a demonstration or some more protracted thing where students don't have ownership or they don't have that level of visibility over what we're doing and why because it's spread out so long or they don't have that ownership piece that we talked about earlier. Last piece, what materials and prior knowledge do students need to be successful? So this is the absolute last thing. So before I decided to use tennis balls, had to decide all these other things, right? Now, the very last piece is, do we use tennis balls or marbles or stuffed animals? Okay? The very last piece is the materials and prior knowledge. And the thing about prior knowledge is that it's really just that foundation of some vocabulary and to be able to picture what we're talking about. Okay, so coming to your lessons, so STEMifying the lesson. Using all of this. This is from, and you can look it up if you'd like, this is a grade 3 model ELA lesson for Common Core off the DESC's website.
Just out of curiosity, how many of you are aware that the DESC now has many, 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 many model units? Okay, so some hands. If you're not aware of that, on the Department of Ed website, a big part of their Race to the Top funding was they developed model curriculum units, and then by grade level and subject area and so on and so forth. And as Francis said, it was an attempt to kind of group standards in a way. That was sort of the department's attempt at grouping standards. So these can be accessed, if you kind of go to probably here of the website, that stands for curriculum and instruction, by the way. If you probably go to like that of the website, that would take you out to all of these model curriculum units that are available on the Department of Ed website.
So in lieu of scrolling through lots of pages, just pulled out some key things here. So when looking at the content areas, so this is a model lesson for ELA, but they've included history and social studies. And it's a unit, whose story is it anyways? The craft and structure of writing about history. And they have, you can see here, they have some history, social studies, and ELA standards. So what they want in this lesson, and if you're going to go back and look it up, I think it might be lesson 3 or 4 within this unit that they've put together. First standard, use information gained from illustrations and words in a text to demonstrate understanding of the text and how key events occur. And notice the examples they give. Maps, photographs, where, when, why, and how. Okay? These are all things that will relate to science, and we'll see how that comes together. Number 2, compare and contrast the most important points and key details presented in 2 texts on the same subject. Identify the Wampanoags and their leaders at the time the Pilgrims arrive and describe their way of life. Identify who the Pilgrims were and explain why they left Europe to seek religious freedom. Describe their journey and their early years in Plymouth. Now, what I want you to think about is that weather and water unit again. Okay? Can we use elements of weather and water and precipitation to describe life at the time, where they lived, why they dressed the way they dressed, why their journey was like what it was like? Can we use the images from the text as well as diagrams from science to make those 2 ideas come together? Okay? Can we give examples of how water's cycling through the atmosphere in this text? Okay? So if you go back here, just quickly looking at that, those scientific elements are also key details. Okay? They're elements of their way of life. They're part of those early years. And then you can compare and contrast even to life today, right? Making it even more of an ELA piece. So now the question is what sort of STEM practices could you make a part of this? Asking questions, right? It's how you're going to ask the question, what sort of analysis and interpretation of data that you're going to use, whether it's a combination of taking data from the text, from the images, from the charts, mixing it maybe within the framework that you have in the science unit, okay, or with some familiar tables. Another way of doing this is to look at perhaps examples of the way the weather, looking at the time of the year and the type of the journey or weather on the voyage, and comparing that using weather data that you can get right offline for the places that they left from, or the track over the ocean that they took. Constructing explanations, right? Engaging an argument, and obtaining and evaluating information. The other ones you might be able to work in there too, but they're a little bit harder. Again, that we're not going to go into all the nuances here of the new math standards, but just to show you, this is one artist's rendering of how they're presented, because they are in different forms from Massachusetts, but they're all the same standards. This is really helpful, because right down the bottom you can see that they've already tried to give you some of the ELA and Math Common Core standards that you can't help but trip over doing these if you're doing them, literally doing them, okay? So what you might want to do, one strategy I'd suggest, is that if you have something with you, that you have ELA or Math Common Core standards already assigned to whatever this lesson plan is that you've brought, that you go through and try and find them, and then look at some of the standards, which is up top, that's the standard, and the disciplinary core ideas and the science and engineering practices that you might be able to put in to that unit. And one of the things you may find is that as you're going through, you might not be able to do that. And that can be okay, that's okay. But if you can't, it might come back to that, if we're using tennis balls, but we could change to stuffed animals and get a better outcome, maybe there's a tweak that you can do there, okay? Just by potentially changing the method of questioning or the type of data, or maybe an auxiliary piece of what you're doing, okay? Did you have something you raised?
No, go ahead.
Any questions on this so far? No.
Is the idea of bringing the standards together making sense? Finding those efficiencies within, and you can see that the state is starting to do this for you, in the sense of they're realizing the importance of it. When you look at the science standards here, the fact that you've got the reading, ELA literacy standards and the math standards on the bottom, in the model curriculum units, they're trying to, in an attempt to put these standards together for you. So this work is starting to occur at the state level, certainly. And so I think it's a great indicator for the educators, the people on the ground and the people in the field, that, hey, the state is identifying this as an effective practice, so to speak. So it's certainly something we should be engaging in within our schools as well. And the more we can do that, you start to find those efficiencies. I think the one thing I say to staff all the time is that everything has changed in education. We know this curriculum, instruction, assessment, pedagogy, everything has changed. The kids who are in front of us, right? The one thing that hasn't changed is the amount of time we have with the kids, right? That hasn't changed. That's still the same, and it doesn't look like it's changing anytime soon. And so how do you find more hours in the school day? Well, the way you do that is you find efficiencies within the school day, and you try to make some more of these connections, and you connect these standards to each other. So when you're delivering units and units of study, you're doing it in a way that's touching upon a number of different ways at the same time.
So maybe the thing to do is take a quick look through the green bag at what we have, because you have copies of the new standards in there and a bunch of other stuff. So maybe
Do you want to walk them through the bag?
can we get a bag up front? Sorry. Okay, so what you've got in your bag here. Some folks had asked for more bookmarks. So you have like 25 there. You can give them to your class or your friends or whatever. Your evaluation form. Hopefully yours are in the same order as mine. Disciplinary core idea progression matrix. Okay? So this is disciplinary core ideas, this box in the corner. So this is from DESE that shows a matrix and how those ideas sort of evolve standard by standard or over time, okay, according to the grade spans you're traditionally used to. Okay, so that's when you look inside here.
That's sort of a staircase idea. It just builds and builds and builds.
The next piece that you may have in there is the draft revised Massachusetts Science, Technology, Engineering Standards. These are all laid out just like what you see up here. I was just looking through. And they have not assigned Common Core standards to all of them.
Right.
Okay? Now, these are arranged, and like I said, they're trying to kind of take a crude approach at a grade-by-grade narrative. Unfortunately, without adding a lot of time to discussion and reading, if you go through all of the background documentation, what they've given you grade by grade is a minimum of what a student should be able to do to try and create a narrative grade by grade. This is not curriculum, and they do not intend that this is the only thing you do. And actually, they are explicit about saying that it's not good to only do this as well. So the danger here that I think the state's going to find out, unfortunately, over the next 6 or 8 years, is that by publishing this grade by grade, unfortunately, folks are going to look at that and say, you know what, this is what I need to do. And if I do this, that's actually what the guy before me should have done, or if I do that, that's what the guy after me should be doing. And it's going to kind of shape people's thinking away from the type of narratives you need to be thinking about. And they're going to have to, once they figure that out, they being the state, are going to have to somehow figure out some messaging to correct it. So don't fall into that trap, okay? Because there's a lot of good evidence that doing the 3 units a year doesn't work. Just look at the state's data. That's what most people do. 3 units a year, sort of in isolation, and while there may be some vertical narrative to it, that long-term spiral doesn't work. So beware. Value of cross-cutting concepts. So what they've done is they've taken those cross-cutting concepts and they're sort of implying them. And they've been sort of mixed in. That's what that document's about. The case for an integrated approach, that sort of talks about what we just talked about. And then there are some different, oh wait, there's another one here. This is a comparison, and it's very tiny. You're going to need your magnifying glass, and actually probably give those to you. This compares the current grade level bands to what's going to be the next generation of Massachusetts frameworks, and then explains it out in detail in the inside. So that'll be fun reading.
And then the last part of your bag, we had a lot of requests for materials, like actual what a unit might look like, or what different materials might look like in terms of, for students, readers around light waves and different lessons and stuff. We had access to no-atom materials for obvious reasons, so that's why you have these materials in your bag. In response to folks who would ask for, can I see what a lab manual looks like? Can I see what a student reader might look like? So these are just some resources to give you an idea of what exists out there in the world in terms of trying to achieve these due next-generation science standards. And you can use these as a jumping-off point, certainly, as you start to think about some of the units within your schools and within your classrooms.
And in the corner down the bottom, you'll see a little number, like an E4 or something like that. That's the grade level. So M6 would be grade 6, E4 would be grade 4. So that's just some exemplars. So taking those standards, okay, and you can look at, I would focus really with that standards document. And I'd pull out one of those. Let me pull my standards document out here. I'd pull out the standards document.
So
and
you
I'd
want
pull
everyone
out.
to have that in front of them right now?
Yeah,
Have
if you
that
can
in front
grab
of them?
that.
Yeah.
Grab a bookmark. And then you were given those 3 slides from UBD, big blown up when you came in. Okay. You want to use those pieces. So use the 3 slides, start at stage 1, take your lesson and look through those questions on stage 1, Okay, when you're looking at the STEM practices and processes, you can find those practices on the bookmark. Okay, you can go through, look at your grade level, since they've broken these out roughly. I mean, they're by grade level, but you can access them on a lot of different levels. And just see if any of the ELA and math standards, if you have them already broken out on that unit, if you can find areas where they cross over, okay? And sort of work your way through those 3 slides with your lesson. And the thing is in order to do this and get some feedback and everything, get back with the group that you started with. So the number that's on your name tag, okay? And if you ended up with a group of 2 and your partner disappeared because of the snow or something, just you can merge with another group. If you don't recognize the people that you were with this morning, go stand by your number.
So before anyone moves, just because we had some rustling of papers and things like that there, can you just repeat those directions again so I have them in my brain?
Yeah, absolutely. So you're taking those pieces, standards, bookmark, the 3 slides, okay, and your lesson, and you're going to meet with your group. Go through your lesson with the slides, and then talk with your group. Explain about your lesson, okay? Because what's going to probably happen is you're going to find you have some of what you need and other things that you don't need, or you might, sort of like when we were trying to tackle this room, first couple minutes, you're going to be trying to figure out a plan of attack here, okay? Go through and you can talk with your team and kind of maybe brainstorm some strategy as to how to best go about looking at that first slide.
So if I brought a social studies lesson with me, I'm going to sit with my group 5 over there, and I'll use that document from the Department of Ed to figure out what sort of the science standards I could bring in to that social studies lesson? Is that the plan?
Yeah, exactly,
Okay.
exactly. So looking at those, and if you have a social studies lesson and you want to look purely at the practices, that's fine. But what you're trying to do is you're trying to look at how you can take that the ELA lesson, the math lesson, the social studies lesson, and bring science standards, practices, processes into it. Okay, it doesn't have to be all of the above. But what's nice about the way these standards are broken down is that you can see right in these boxes practices, disciplinary core ideas, and even some hints on what Common Core standards relate. Okay?
By a show of hands, how many of you brought a lesson with you?
Okay, great.
Okay. So what we'll try to do is, hopefully by default, every group will have at least one person that brought a lesson that you can kind of talk about and work on as a team. So let's just say Paul brought a lesson, and he's in a group, and no one else brought the lesson. Everyone else is going to have their bookmark with their practices on there. Everyone else is going to have their science standards. And Paul's going to say, I brought this lesson, and people are going to say, here's a connection you can make to it. Here's a science practice that you could have brought into it, and so on and so forth. And you have that dialogue. If more than one person in the group brought a lesson, you do that for that lesson as well.
And if I came, I'm sorry.
That's okay. And then I think we'll probably do a sharing out afterwards to kind of figure out, here was my initial lesson, and here's how I STEMified it, either by incorporating the practices and processes from the scientific method or the engineering design process, or by literally pulling in standards from the science frameworks.
So if somebody was in your group and they showed up with this, literally this, saying, I want to STEMify this, what would be the first thing you'd ask them? What's the standards?
Right.
What's the purpose of it, right? Then the thing is like, well, what practices or processes are involved in that? And if they say, well, I don't know. Okay, that's where we're starting from, okay? All right, go
Everyone
ahead.
clear on the task? Okay, go ahead. Meet up in your groups from this morning, same spots, so on and so forth. Bless you. All right, guys, we're going to pull back. If you could just stay where you are, just kind of park where you are so you're with your group. And we want you to kind of stay in your groups. And can I stop you guys up there? Thank you very much. Just kind of hang right there. And let's just kind of report out. What are some things that you talked about in your group? What was the lesson? Were you able to STEMify? That was part of the conversation I just had with a colleague from another school district over here, in the sense of not everything will be able to be STEMified. I think that's an important note to make as well. It has to be a natural fit. You just can't randomly put stuff together just for the purpose of STEMifying something so you can STEMify it. So I think you need to have that kind of running in the back of your head as well, that when you STEMify something and you find these efficiencies in what it is that you're teaching and what it is that you're trying to get the kids to understand and learn, you want them to be natural connections. And I think you were just saying in some of these programs that are out there, you have a lot of unnatural connections, correct?
Right. So for instance, most programs that you get out of the box, they're engineered. They're engineered either as a bunch of resources that you have to kind of pull and figure out, or they're engineered to have certain leveled reader extensions as part of it. And so those sort of things there becomes a point where it's engineered in a way that you can't do a whole lot with it. And that's the unfortunate part of some of these programs. And that's where we start to run into these time on learning things where it's like, well, you've got the math program, right? And then you have to jam that in next to the reading program and then the science program. And so, that's the trick. But back to that idea of, you want to be doing things that are purposeful. So in places where you have flexibility to be able to either swap things out or to replace one element with another. So for instance, if there's a reading program that has nonfiction readers that are a part of it, chances are, if you have a good science program, you have nonfiction readers that are a part of that. And so if you can use the nonfiction reading from your science program in place of the one that's in your reading program, now you can do two things with one stone, and it becomes more relevant because you're reading about science you're doing instead of reading about something that might be related to what you're doing with a completely different vocabulary, with completely different processes that doesn't really tie in tightly. So that's one way of dealing with those kind of programs. And the kind of, hopefully maybe some of the tweaks that we see coming out of here is that, like, let's say that there was a social studies standard related to, I'm just going to make this up, related to a historical figure that, a particular Massachusetts historical figure, something like that, researching. So maybe it was like some kind of quasi-ELA social studies thing. If you have leverage to choose the figure that you study, you can choose, potentially, a Massachusetts STEM figure. And so now that you can kind of look at not only a historical person that made maybe some community impact, but a historical figure that made a community impact in science. And then maybe going further in that to a particular area of science. Maybe it was electricity. And some of the fabled Ben Franklin sort of things. Mm-hmm. That's sort of an idea. But anyway, I don't want to get too off the topic because we're reporting out.
Yeah, so group share. Someone start us off. What did you discover? Were you able to STEMify something? If you were, what was the lesson? How were you able to STEMify it?
Mm-hmm. And that's a big argument against a science specialist model. A lot of people, and I hope we may have some people here from STEM schools. Every time I hear about somebody starting a STEM school, the first thing they say is, and we're going to have a science specialist. And the science specialist is their whole job is going to be to teach science to all the kids. And the flaw with that, one is that one person teaching all the science for all the kids in the whole school mathematically doesn't boil down to a whole lot of time. But the other problem that you run into, even if you have sort of more of a middle school model where one person does science, one does ELA, math, so on, what happens is you are now putting barriers up between those disciplines, which are not only, they're on so many levels. Their time, their perspectives, their lesson planning, and all of that. So when you're an elementary teacher and you have a self-contained model, you have exactly what you're identifying. You have so much opportunity to really make all of this content in all the areas so rich and interconnected. And that's one of the, I really believe that that's one of the reasons why you see the data drop in middle school, because students go from that sort of environment into an environment where they see all these different people who don't necessarily have the time to connect, who don't necessarily have all of this planning across what they're doing. And so it becomes more disconnected, yet everybody has different expectations of the students. And the student, as an experience, as a user of that experience, it's a lot of shock.
Particularly coming out of 6 years of one experience,
Yes.
you know, where it's very predictable, and now you a big change.
Yep.
Other things, topics, things you were talking about in your groups. What was the lesson? How did you?
Or how about this? How about stage one? What were you finding in stage one? When you were looking at what you brought, did you find any challenge with the standards? Or did you find that a lot of times, you know, it's possible, you have something and you were creating it to fit a need, but it wasn't necessarily derived from a specific standard. It was more derived from a specific need. That can happen. I mean, did anybody find any of those things in their group? Did anybody approach that issue maybe through an assessment? So maybe, you know, you can come up with all these standards. It's easy to associate an ELA standard to a STEM standard or social studies standard. But I think about the dreaded worksheets. You know, you have some sort of like an assessment tool that you're using, and usually there's a context to that. Did anybody see an opportunity to maybe change the context of an assessment or the context of I guess I would say the context of an assessment to maybe better align it to an objective that included STEM in there or some STEM practices?
How many of you was this very difficult to do? How many of you found this a challenge to do? Okay, maybe about half. How many of you felt it came pretty easy? So the other half of folks who didn't raise their hand for challenging, how would you articulate the process? Go ahead. Okay. Okay. Good. Yep.
One of the challenges I considered in my own mind was that a lesson, you could have a one-day lesson.
Mm-hmm.
That you're thinking maybe this is a lesson, and then to maybe science and engineering could come across like another day, another
Right.
lesson, so another extension. So now my one-day lesson is turned into a two-day lesson.
Mm-hmm.
And so you have to be willing to give up time somewhere else to do that. So that was something that I thought about the whole time I was lesson. This is an entire lesson in itself. So I'd have to either cut down the lesson and it wouldn't be as rich the first time,
Yeah.
or extend it into another day in order to bring practice up.
Yeah, that's an interesting struggle. And that's a real struggle. I mean, like the struggle you mentioned, that's a real struggle as well, right? Do I pare it down or extend? Right?
And I think the strategy that eventually emerges there is you've got your ELA lesson, and that takes this block of time, and you've got your science lesson that takes this block of time. But if you make sort of like a plug and a socket, you know, if you create in your ELA lesson the connection to the science, what you're really doing is you're borrowing science time for ELA and you're borrowing ELA time for science. And I know that, like, boy, wouldn't it be great if it was just that easy? But that's the unfortunate longer work of getting it perfect, right? Which you never ever get it perfect, but it just gets closer. But I think that's really that strategy there. So, like, when you think about scientific writing or journaling, that's ELA. So if you're doing journaling in another area, can you incorporate scientific journaling instead of some other element of nonfiction?
And I think what's really encouraging about the two struggles that were mentioned, if you you know, again, I think in pictures, and if you think of this thing that we're doing as a road, right? Well, way down here at the start of the road are people who aren't even thinking about this topic at all. Like, it's not even on their radar, right? And they're kind of down here. So you're grappling with some stuff that's putting you up here on the road somewhere. So that's actually pretty cool. So the fact that you're struggling with this As weird as it sounds, is actually a good thing because you're thinking about it, and you're thinking about change, and you're thinking about what I can do. And if you look behind you in the line, there's a long line of people behind you who aren't even thinking about this stuff right now, right? So as you continue to move forward, and you kind of think, and maybe you resolve it a little bit, and you resolve it a little bit more, and you resolve it a little bit more, and before you know it, you're over here living in this world where it's starting to kind of come together. So I think don't be discouraged by the struggle, because the struggle means you're making progress, and the struggle means you're moving down the road somewhere, and it's putting you miles, in some cases, in front of other people who maybe aren't even considering these things right now. So that's good that you're even thinking about it. Does that make sense? Okay.
Yes.
I think jump off of that, Scott. One of the things that you have to think about is that we're practicing this.
Yes.
People are saying that some lessons lend themselves better to others.
Yes.
And that's the door that's opening.
Correct.
Okay,
So go through it.
Where to start?
Yeah.
Exactly.
Go through that door.
Exactly.
Yes.
and then later down the road, you're going to start, your lens is going to start refocusing.
Yes.
You are going to find ways with the lessons that are more challenging or a struggle now. The more practice you have with the lessons that lend themselves well to it,
Correct.
just push you further down that road in the right direction.
100% agree. Remember the happiness video we watched?
Yes.
And you can rewire the brain. And our brain always scans. I was at a thing the other day from a different guy, and he put a picture of a T-Rex and flowers up, right? What's the picture everybody looked at? The T-Rex. Your brain goes to oh God, there's a T-Rex picture, right? Does that mean there's one around? And no one looked at the beautiful flowers. Your brain just automatically goes to that negative. And finding the opportunity for where you can do it will retrain your brain, and you'll be scanning the environment in a much different pattern if you start to do those things. Right, so go through the doors that are available to you to go through. Totally agree.
And the kids will help you. That's the thing. As you go through that process and your lens is changing, their lens is changing. And that will make it easier for you to do some of the changes you need with things that are a little more complex in other areas. And it'll become more apparent to you what your expectations are of them and what they can perform. I saw one here and up there. Yep. Yep. Right. And those are great examples. Process writings, journaling, using the scientific method. That's a process writing. Persuasive writing. That's an evidence-based conclusion. Right? Supporting your claim with evidence and writing it in a persuasive manner. All of those things are two. Yeah, and I think someone else down here mentioned that. That idea that a lesson equals a day, you've got to get away from that. The thing is that a lesson represents what you need to do. That's what you need to accomplish around these concepts, around these skills, and using those resources and tasks. So it's a segment that you're doing. But the lesson itself may take 2 days, or may take potentially 3 days. You have to be prepared for a lesson to end up sort of segmented like that, especially in science where, in one unit you're going to be growing plants, and that's going to cascade. You can't make a plant grow faster than it naturally grows. It does what it does. So you need little side strategies of, that maybe that plant is going to grow and you're going to make daily observations in the morning, but you're going to continue on to something else that's next in that lesson 2. Or there's other things where, in order to do your reading and have your discussion and have students work in teams, that's going to be, reading's going to take 20 minutes one day, and the discussion's going to take 20 minutes the next day or after lunch, and then, that's all part really of one lesson, but it may end up in segments. And I think that that's one of the difficult things as you start to work this way with lesson planning, is that the nature of schools to have all these little scheduled boxes, it doesn't always work that way. And actually, usually, it doesn't work that way.
Yeah. So maybe we should jump
Yep.
ahead, I think, time-wise.
Yep. Okay, so just jumping ahead here a little bit. So the example, okay, we already grabbed this. A couple quick things that you find with it, and we're already kind of talking about this. Common little curriculum pitfalls. Isolated concepts, it's death to the concept. So that's, again, bringing it back in, connecting it to the ELA, connecting it to the neighboring lessons. Another common curriculum issue is not focusing enough on the synergies. I think we've gotten that across, making sure that what you're doing is hitting both levels. And I think the number one thing for me on this list is being overly focused on prior knowledge at the cost of students being able to try to be able to do the whatever it is, to be able to experience it, because you're not going to be able to give the students homogeneous background, and it's just not. Some students are going to be ahead of others. They're going to have gone on vacations to some volcanic island, and others won't. You know, unless you're going to take your whole class to the volcanic island, you're going to have to do what you can do. But what you need to figure out is, like, what is the minimum viable base? So what's the minimum viable base that you can operate off of so that the students can begin to start experiencing, to begin to start doing and trying and working through those practices? And that's where you really get authentic problem-based learning, because you're throwing out a question, you're throwing out a problem as part of this process, and students are able to try and do it. If they're not trying and doing it and you're just focusing on the background, you'll never get there. Okay? Sorry, so it's an issue that people do not leverage authentic problem-based learning. So a lot of times, how does that sort of play out? People will try to create tasks that everybody comes up with the same outcome. Without a doubt, you're going to come up with the same outcome. Sorry, I don't know. Someone asked that question. I don't even know where you are. Okay, here. So, yeah. Oh, sorry. Leverage means to just use. To use or make use of. Yeah. Yes. Yeah. Well, it's not authentic. That's the thing. Is that? Yeah. Exactly. So the thing is that that opportunity for students to try riding the bike and to skin their knee in a safe environment, right? You went up to the STEM companies and you saw people using elementary STEM skills to feed their families. That's a much less safe environment than being able to do it in a classroom where you can get help to build a skill to be effective. A lot of people focus on creating tasks that have a clear and defined outcome that's black and white, and then just kind of go on. But that's actually an opportunity you can use. So if I don't want to be misleading, that's something you do want to do. Create authentic opportunities for. Somebody called it the other day positive failure. So that's a good thing. Positive failure is a good thing. Okay. I think we already. A couple just quick things with and if you're in on this webinar tomorrow or Thursday, you'll get this. But a couple key changes. The literacy-only approach isn't sufficient under the new standards for sure, because you're not going to be able to function off of knowing the definition. You can only get so far with that. Hands-on approach in and of itself is not sufficient, because doing something hands-on does not necessarily mean that students are engaging in any of those practices. Okay, they're not necessarily developing the model. They may be actually working hands-on off of a sheet with a step-by-step pictures or something. If you've worked with Lego robotics, oftentimes they come with these little primer documents. Build by number is kind of what it is. Well, what's the value of that? It's exciting. Are you putting things together? Sure. But if a student doesn't have that sheet, it changes the game in a very big way. And that's really where they need to be, not building by number. I can paint by number, but I'm a really poor artist. And that's what we need to get to, is that almost an artistic skill, right, with these practices. So that's where we come into the real inquiry, because inquiry, we're problem solving, we're answering questions, and that's only sufficient. So it can be hands-on, it can have literacy elements to it, but it's only sufficient if the students can develop and demonstrate those STEM practices. So the major change really under what's going to be the next generation of math standards and next generation is that learning is now, and don't read too far into the word ability. We're not talking about intelligence here. But learning is now the ability to do. It's the ability to demonstrate the learning. So if a student can't demonstrate it, it's not learning, sort of under this new definition. So that's a big change. A couple other quick things here. The scope creep, I think, is the one big takeaway here. In looking at the units and trying to STEMify them, you can kind of see this start to happen. If you're just doing it, it doesn't really have a purpose, you start to get scope creep. A lot of times this is where sort of the learning about weather and climate becomes learning about Antarctica, becomes learning about penguins, becomes doing the penguin play, becomes doing the whale drawings, and that's, if it has a standards backing and it belongs in those other areas, that's great, but be mindful of scope creep. And the law of diminishing marginal returns just says that just because you do it over and over and over doesn't mean that it's creating more value or sufficient value for that time. Because usually what happens is that you get less value for the same amount of time because the students stop buying in, or they say, oh, I've done this before, even though you're like, no, you didn't do this before. If they view it as I've done it before, diminished return. So that's where this kind of melding together of ideas.
One of the teachers in the district where I work made the great analogy to sort of the nutritional value of a lesson, right? When you think about putting a lesson together and you think about food, if the lesson is Doritos and ice cream and candy and cake, right? Those are food items, but there's not a lot of nutritional value in those food items. But if the lesson that's put together is, proteins and fiber and fruits and vegetables and things like that, metaphorically, and kids are getting a lot of nutritional value out of the lesson. And so when you think about the activities and the ideas and the things that you want to plan as you put them together, what's the nutritional value that the kids are going to derive, the nutritional learning, so to speak, that they'll derive from the lesson that you put together? So very similarly in terms of planning a meal, right? Planning a lesson is the same thing in terms of what your body can use from that. This is sort of like what your mind can use from it.
Right. And so these new standards, as you're kind of going through it, don't be practicing practices. If you find yourself practicing practices, that's not helpful. What you want to be doing is you want to be creating units where students have opportunity to interact with all the parts, but maybe there's certain parts that they have more ownership over, and that the standards, and these are all things that are quite almost literal translation of what's in your excerpts from what's in your bag there. But the standards are not curriculum. So while you're going to be seeing certain standards the way they're formed now, as almost, you can picture the task and all of this, in and of itself, it's not curriculum. So this process is figuring out how it fits into your existing curriculum or how you change that through some of what you're doing here to get the internal narrative that works for you. So that's where the standards narrative, you'll see the word narrative used, and they break out grade by grade. That narrative that they're giving you is just a segment of sort of a larger year-long narrative that you need to build on your own. And that's their way of creating a minimum of exposure for these kids, because they're finding that it's so fractured, and that what goes on in Boston and what goes on in Wenham and what goes on in Beverly, and everybody has their own thing. And so if they can give a minimum, then it brings all those things a little closer together. Okay. And the idea of perfect recall from grade 3 to grade 5, that's one of the catches in this. If you look at the narrative, the vertical grade by grade case they make, you can fall into that trap of thinking if I do it in 3rd grade, they're going to remember it in 5th, and that's clearly not the case, and it's not the intention either.